Hello everyone, I hope you are doing well. So in this video, we are going to discuss Geeks for Geeks problem of the day, and today's problem is express as sum of power of natural numbers. So the problem name is pretty big, but it is a medium level problem. So if at the end of this video, you feel that this video was helpful for you, or if you were able to derive any value from this video, then consider dropping a like, and don't forget to share your thoughts on the problem statements or any general thing you would like to share. You can write it down in the comment section, as your engagement with this particular video really helps the YouTube algorithm to understand that this video is actually helpful for you, and it will be able to recommend this video to more people like you who want to keep solving new problems. So let us quickly start the problem statement. They say that we have been given two numbers n and x, and we have to find the total number of ways n can be expressed as the sum of xth power of unique natural numbers. Right. So there are two things. The first one is the xth power, and the second one is the unique natural numbers. As the total number of ways can be pretty large, we have to print the number of ways modulo 10 to the power 9 plus 7. Right. So this is our whole problem. So let us see what we can do in this problem. So let us take the first sample test case. Right. So the first thing that I see with this particular problem is I need to somehow make the sum equals to 10. Right. So the value of n is 10. I need to somehow make the sum as equals to 10, and I need to do it using natural numbers. So let me just first write out the natural numbers raised to the power this particular x. So I will write all the natural numbers raised to the power x. So the first natural number is 1. 1 is power 2 is 1. Then we have 4. Then we have 9. As soon as I try to write 4 square, it will become 16, and it is greater than 10. Right. So it is obviously not valid to consider this particular number. So in this case, I only have 3 numbers. Right. I only have 3 numbers. For each number, I can either decide to take it or not take it. Right. I cannot take any number multiple times. That is my question, because I want unique numbers. So I have 3 numbers now, 1, 4, 9. I want to take some of them. I don't know which one of them I want to take, but I just know I want to make the sum that equals to 10. And now I want to find the number of ways. So like if you have done some problems on DP, you would clearly see that this is a very like standard DP problem where you have been given some elements. You can only take each of them once, right? Either you want to take it or you don't want to take it, and you have to make the total sum equals to 10, right? So this has been reduced to a pretty standard DP problem. Now let the value of, like, let's say n was greater than 10, let's say it was somewhere around 50. So now you will have to extend this particular array. The next value can be 16, then 25, and then 49. Right. This is how you are going to extend the array. You have to extend this array until this value is less than or equals to value n that we have been given. Now, if we try to write all of these values like this, what will be the worst case complexity? Let us discuss that. So the value of n at max, it is small n, that has been given to us in the problem statement. It is at max 1000, and the minimum value of x can be 1. Right. So in that particular case, you will have to write all the numbers raised to the power 1. So I'll write 1, 2, 3, 4, 5, and so on up to 1000. Right. So there will be 1000 numbers, a total of 1000 numbers, and you have to form a sum of 1000. Right. So a DP state will look like, in the worst case, DP will look like 1000, 1000. So let's say this is I, this is J. So I will be denoting the index of number that we want to take, or we are considering whether to take or not, index of number to make decision, right, whether we want to take the current number or not, and J will be the remaining sum, So this is going to be an n square dp, and let's see what happens at each of the states. Let's say you are at a dp of ij, right? So if you decide to take the current element at index I, you can only take it when v of I is less than or equals to j, because otherwise if v of I is greater than j, if you take it, j will become less than 0, and that is not possible. So only if this is true, I'll take a variable, let's say x, I'll mark it as dp of I minus 1, and since I have used v of I, I'll subtract it from the sum, remaining sum, right? Another way is that I don't take it, so there is no condition on it. I can just directly write y as dp of I minus 1, and since I have not taken the number, the sum will remain the same. So dp of ij will be equals to x plus y, x plus y, right? This is like very straightforward and simple DP. Now what will be our base case? So only when I've reached at index 0, I have considered all the numbers and my remaining sum is 0, right? Only in this case dp of I like 0 0 will be 1. So this will be our base case, and for all the others 0 and I, our dp of like dp state will be equals to 0, right? So these will be our two base cases. So this was all about today's problem of the day. Let me just quickly summarize it and then we'll have a look at the code. So first of all, what I did was I just wrote down all the natural numbers raised to the power x until that natural number up raised to the power x was less than equals to the value of n that we have been given to us. Because even if I take further, it is no use of taking it because I cannot subtract it from my number. Now in the worst case, we discussed that I can have a total of 1000 numbers because the n value of n can be 1000 and the value of x can be 1. In this case, every number will be raised to the power of 1. Now my DP states will be of n square format, and in the worst case it will be 1000 into 1000. So the first state I is denoting the index of the number at which I have to make a decision whether I want to take the current number or not, and j is denoting the remaining sum that I have left with, right? So I can only take the current number when v of I is less than equals to j. That means the remaining sum should be greater than equals to v of I. Only then I can remove this particular v of I from my remaining sum. So if I take it, my DP transition will look something like this, where x is equals to dp of I minus 1 and j of v of I. Now if I don't want to take the current number, my transition will look something like this, where y is equals to dp of I minus 1 and j. Now dp of ij will be equals to x plus y. So it will be equals to the summation of both the ways that I have explored, right? Coming on to the base cases, 0 will be the index when I have traversed all the indexes and I have decided for all of them whether I want to take them or not. If after traversing the remaining sum is equal to 0, then it is a valid condition, otherwise it is a not valid condition, so I store 0, right? So before showing the code, let us discuss the time complexity of this particular approach. You will see that there will be two loops, right? Two nested loops for I and j. So this would be n square, right? In the worst case, it will be n square. And since we were also maintaining this array where we are calculating for each natural number its raised to the power of I, let us say we are using an efficient method like binary exponentiation. So in that case it will be log n, right? Only if you are using binary exponentiation, or even if you don't use it, the value of x is only 5, like the value of x is only 5, so you can easily calculate the the power in constant time, because you just have to write, for example, if you have a natural number I, you can calculate I raised to the power 5 like this. So it is almost a constant time operation, right? Otherwise you can also choose binary exponentiation, and in this case the binary exponentiation takes log n time, so total complexity is n square log n. This will be the time complexity. So let us have a look at the code now. So what I have done is, this is my binary exponentiation function. Even if you don't do this, let's see, there was something somewhere written, right? The value of x is only up to 5. Even if you don't use this, it will not make a huge difference. So like we have initialized the value of mod width in its power 9 plus 7, right? And I have initialized my empty vector v with a single value called 0. Now for all the natural numbers, I'm trying to traverse the natural numbers. If the value of I raised to the power x, so this is my expo function which I have defined here. You can check it out, but I'm not going to explain it because this is a standard binary exponentiation. So this condition should be satisfied that I raised to the power x is less than n plus 1, and I just increment I. Whenever it is less than n plus 1, I just push it back into my vector. So now in the vector, I have all the elements that I want to consider. So I just calculate the size of the vector v, and I calculate my dp of size comma n plus 1. Right, I mark my dp of 0 0 as 1, otherwise all the other values will be default 0. So for all the values, I just traverse through the size. So this is the size of the vector v, right? Now for the jth loop, I just traverse through all the possible sums that are possible, and I create two variables, take and no take. Take will be storing the result when I want to take the current element, and no take will be storing the result when I don't want to take the current element. So if j is greater than equals to v of I, I would want to take it. So I would go to I minus 1 and subtract this particular v of I from my j value. If I don't want to take it, I just go to dp of I minus 1 comma j, and the dp of ij will be equals to take plus no take and modulo, because they have asked us to do this. At the end, I can just return dp of size minus 1 comma n, right? So size minus 1 will be the last index in the vector v, and n is the total sum that we want, right? So this was all about today's problem of the day. Let me just run and show it to you that this works. So you see that it passes all the test cases. Now some of you might be wondering that the expected space complexity is O of n here, right? But we have used n square space. So why is this so? Can we reduce it to O of n or not? So in problems like this, you can easily reduce it to O of n. Let me just show you how. So you will observe that for each of the dp states, it is only depending on dp of I minus 1. Let us not talk about this second part, right? But it is depending on I minus 1 state. All the dp states, there are no complex dp states, right? It is only depending on I minus 1, right? So what we can do is we can maintain two independent arrays. One will be the previous array and one will be the next array. So let me just show you. So let's say this is the 0th array. You have all the n plus 1 states here, and you calculate the array for index 1, right? So you will have two arrays right now, right? So since the values of this particular array is only depending on the I minus 1 state, I can easily calculate all the values from here. Once I have calculated all the values, I will replace this old array with this particular array, and my new array will be empty again, right? Since I have the details of the 1th array now, I can easily calculate for the second array all the values from here. Then I will again replace the previous array with this particular array, and I can calculate for 3, and this can keep on going on. So at the end, I will only need 2 arrays at a time, and that would be approximately O of n. So let me just quickly show you that that approach also works, so that we have the most optimized approach. So let's say we don't have a double dimensional dp, we will only have dp single dimension, and it will be only dp of 0 equals to 1, right? So let's say I've reached a new ith state, so I'll form my, let's say, vector end new dp, and it will be of size n plus 1 and 0, right? This is what we have now. So now at this particular state, my take will be equals to dp of j minus v of I, and this will be equals to like this. So you see, I've removed the I minus 1th state, right? All the other things are same, I've just removed the I minus 1th state. Now the value of new dp will be equals to this particular value, and after I have completed all the things, my dp will become equals to new dp, right? And at the end, I don't need this size minus 1, I can just return dp of n. So let us compile first. Let us see that we don't have any compilation error and it works. So we have something, yeah. So new dp will only be a single dimension array now, right? So let us just see that it works, if it works now. So it is passing like the sample test cases. Now let us try to submit it. So you see, since each of the dp states was depending only on one state and it was only the previous state, so we just maintained a single dimension dp. We will have two arrays. So new dp will be the current state and dp will be storing the previous state. After I have done all the things for the current jth iteration, I'll update my dp as new dp, and at the end I can just return dp of n, right? So this would be the most optimized solution in terms of space also. And you can always do these types of optimization like whenever your current state is only depending on the previous few states, right? So you see that it also passes all the test cases and the solution works. So I hope that you guys were able to understand the solution. If you guys did, then consider dropping a like on this video, and don't forget to subscribe to this channel. I see a lot of people who watch these videos have not subscribed yet, so if you are one of them, then do consider subscribing. It's always free of cost, and you can always unsubscribe later if you don't find the videos interesting. Until the next video drops, keep coding, stay safe, bye bye.